Hello, Year 11, and welcome to the next exciting class involving calculus and differentiation. I know you're tremendously excited by this whole concept, so let's see if we can make sense of the next step in this marvelous journey. So we're going to be talking about whether or not we can differentiate something. Now, the process of finding the gradient of a tangent is called differentiation. That means that when we have some type of curve, for example, let's say we have some weird random curve, if I'm actually finding, let's say at a particular point, how steep it is, means I'm finding that's supposed to touch the curve there, I'm finding the gradient of the tangent to our red curve. And at that point there, the gradient of that tangent might be 3, it might be 4, who knows. But finding the gradient of that tangent is called differentiation. Now, most times when we graph things, they'll be nice and smooth and continuous, and they'll be okay. But occasionally we're going to come across things that we can't graph quite as nicely. So one example of this would be the hyperbola. And if you think of what a hyperbola looks like, something like this, and you have asymptotes. The y-axis is an asymptote, also the x-axis is an asymptote, but in terms of our graph, it's the y-axis that we're most concerned with, whether it can be differentiated, because the curve never touches the y-axis. So there are no points there at the point x equals 0, which is the y-axis. There are no points where the curve touches the y-axis, so there can't be a slope on the y-axis. So what we say is this. We say a function, y equals f of x, that just means something we can graph, can be differentiated at a particular point, let's call the point A, if the derivative exists at that point. In other words, you can't differentiate if there is no derivative. You can't find the gradient if a gradient doesn't exist. And this can only happen if the graph that you draw is continuous and smooth at the point that you want to find the gradient. Now, here we've got 3 different graphs. If we look at the first graph, it's not going to be able to be differentiated at A because the graph doesn't come in contact with x equals A. It's an asymptote. If you look at the second graph in the middle, we can't differentiate at the point B because there's a hole there, which means that the graph doesn't exist at point B. It's not continuous there. And if you go to graph C, the graph on the right-hand side, it's not actually able to be differentiated at that point there. It's called a cusp because it's not smooth and continuous. And if you actually look at it, look to the right-hand side of this point here. If you draw a tangent in, it's actually something like that. It's going uphill from left to right. But if you actually drew a tangent in on the other side, it'd be going downhill. It's negative. Doesn't make sense to try and draw a tangent there because it's not smooth. It's a pointy edge and you can't differentiate when it's pointy. So let's have a look at our examples. The first question says, find all the points where this particular function, where this graph below cannot be differentiated, where it is not differentiable. Well, here's our first point at point A, y. Well, it's not smooth. It's got a pointed edge there. Can't differentiate when it's pointy. B, again, it's not smooth. It's got a pointy break there. Not differentiable there. And part C, can't differentiate there because there's a hole there. Nothing is at point C. So they are the 3 spots on that graph where you cannot find a derivative, you cannot differentiate, so it is not differentiable. So the line's not smooth at A or B, it's discontinuous at C, so we can't differentiate it at A, B, or at C. Let's have a look at our second graph now. This is a piecewise graph. What a piecewise graph means is that there's two parts in this case. The first part is we're going to be graphing y equals x squared. Y equals x squared. The second part of the graph is we're going to be graphing y equals 2x plus 3. Now, if I graph y equals x squared, I know it's a parabola that looks something like that. I've actually been a bit more careful when I've plotted this because I've actually gone out 1, up 1, out 2, up 4, out 3, up 9. So I put these points on carefully. So that's pretty good, accurate description of where y equals x squared would sit. The line 2x plus 3, if I was graphing y equals 2x plus 3, whoops, you get the idea there. It touches the y-intercept, or it touches the y-axis at 3 because the y-intercept is at 3, so I'd come here to 3. Has a gradient of 2, so the rise would be 2, the run would be 1, and then it goes something like that. So that would be our line, so let me put that one in. There it is there. Now, we've got too much information showing here because the question actually says I only want the parabola for x values bigger than or equal to minus 1, and I only want the line for x values that are to the left, that are smaller than minus 1. So let's just get rid of the bits we don't need. So if we look at our parabola now, if we went to x equals minus 1, which is just 1 unit to the left of the origin, I've got my parabola that's drawn in everywhere to the right and including minus 1. And that's why that's coloured in there with our red dot, just at that point there, because it includes it on the parabola. If I look at the line, it's everywhere to the left of minus 1, and there's our line. And notice that that green section there is open. The reason it's open is because it doesn't include minus 1, it's just to the left of minus 1. So there's my graph. Well, where can that graph not be differentiable? Where can we not find a gradient? At the pointy bits, which is at x equals minus 1. So quite simply, if we had a question like that, we'd have to be able to produce the graph, find the pointy bit if you like. It's not smooth at x equals minus 1, so it's not differentiable at x equals minus 1. It's exciting, isn't it? That's the end of 8.2. Now, in this lesson, we're doing 8.2 and 8.3. 8.3 is talking about limits. Now, if we're going to learn how to differentiate, and there's two different ways to differentiate. There's differentiation by first principles, as it says here, and there's shortcut differentiation. Now, the first principles we will rarely use. It's a harder method, it takes longer, but we're going to get it out of the way first. It's something that we need to be able to do, but to do it, we have to understand what a limit is. So we need to understand the concept. Whoa, bumped the wrong button there. We need to understand the concept of a limit. Now, what is a limit? Well, a limit's basically used when we want to see what's happening next to something without actually being at that particular point. So, limit's used when we want to move as close as possible to something. This is often near a gap or discontinuous point on a function. Let's see what that actually means. And we'll see, I'm going to answer the question first, then I'm going to describe what it means. Now, when you have limit questions, you can tell it's a limit question because it's going to have lim out the front. And underneath the word lim, there'll be some sort of instruction. And here the instruction says x is approaching 3. That's what that arrow means. When you see this, it means as x approaches 3. This would mean as x approaches 5. As x approaches 0. The arrow means as x is getting close to something. It's not actually at that point, but it's getting super close to it. So in this question, x is approaching 3, and it's a limit question. So x doesn't actually get to 3, but it's approaching 3. Now, if x was actually equal to 3, we couldn't actually put in a value because look at the bottom of the fraction and it's got x take 3 on the bottom. If you let x equal 3, you'd get 3 take 3, which is 0. Can you divide by 0? No, you can't have a 0 on the bottom of the fraction. So that's why we can't let x actually equal 3. But what we can do is we can factorize first. You should always factorize limit questions first if you can. So if we actually look at the question, here's our question at the top. The numerator says x squared take 2x take 3. That's a quadratic. Try and think of two numbers that times together to give negative 3 and add to give negative 2. Well, that would probably be negative 3 and plus 1. So we could actually rewrite that now as x take 3, because x negative 3 was one of the answers, and x plus 1 all over x take 3. So I factorized the top. Now that I've factorized the top, before I continue, is there anything that I can cancel? Well, actually, yes, there is. Look, I've got the bracket x take 3 on the top and the bottom. So let's cancel them. If I've cancelled them out, what am I left with? Just x plus 1. So I've just got the limit as x approaches 3 of x plus 1. Now the next bit's a bit weird, but what we actually do is we say, well, we know x is getting really, really close to 3. Let's think about what would the answer be if I actually let x equal 3. So this bracket, instead of saying x plus 1, would now say 3 plus 1, and 3 plus 1 is 4. So, if you let x get really close to 3, you'd get an answer of 4. This is what it actually means on a graph. If I wanted to graph y equals x squared take 2x take 3 over x take 3, because it cancels down here, it's the same as graphing the line y equals x plus 1, except x can never equal 3 because you can't have a 0 on the bottom of the fraction, which is what you'd get if x was equal to 3. So it's the same as the line y equals x plus 1, but at this point here, when x is 3, the graph doesn't exist. And by the way, when x is 3, what's the y value getting close to? Well, the y value at 3 will actually be equal to 4, and we can see it here on our graph. Now, if that doesn't make sense to you, there's actually another way you can do it on the calculator, and that's this. This is quite acceptable. You can do this in an exam. What you do is you say, well, x has got to be close to 3, hasn't it? Something very, very close to 3. So I might let x equal 2.999. That's pretty close to 3. I could even go further if I wanted to. Could do that. But I'm happy with just 3 nines. I think that's enough. That's pretty close to 3. So you go back to the question, and on your calculator, wherever you see x now, plug in 2.999, because this question is saying let x get really close to 3. So you put 2.9, this is what you type into your calculator. You would go 2.999 squared minus 2 times 2.999 minus 3 all over 2.999 take away 3. And you put that into your calculator and you'll get an answer that is very close to 4. And so you would assume from that that the answer is getting close to 4. Let's try the next question. So this is another limit question. How do I know it's a limit question? Because it's got lim out the front. This time we don't have x though, we have underneath the lim we have h approaches the number 0. So in this question h is going to be very, very, very close to 0. But it's not actually equal to 0, especially not initially, because if h was 0 you'd be dividing by 0 in this fraction. You can't divide by 0. What you do with these questions is you always take out a common factor where you can in the numerator and the denominator if possible. In the numerator, h is common to every term. You've got a 5xh minus h cubed minus 11h. H is common in 3 spots. So let's take out h as a common factor. Notice I still have my limit part. Now I've got h on the top and the bottom. They'll cancel each other, which means I'm really just left with the limit as h approaches 0 of 5x take h squared take 11. I don't have any dividing by 0 problems, so let's just let h equal 0, which means you get 5x take 0 squared take 11, which is 5x take 11. So that's how a limit works. If you wanted to do it an alternate way, you could say, what's a number really close to 0? I could let h equal 0.0001 maybe. And up in this original question here, wherever you see a h, put in 0.0001 and you'll end up with an answer very, very close to 5x take 11. Let's try the next example. You having fun yet? I am. Right, let's go. Oh, this is a bit weird. We're introducing some strange letter, and it's this letter here. Now it's the Greek letter delta, and it means the change in. So delta x means the change in x. You don't really need to know that to do the questions. You just need to realize that there's a funny symbol, and that funny symbol is getting very, very close to being replaced with the number 0, but it can't be replaced with a 0 because if it was, you'd have a fraction with a 0 on the bottom of it, and you can't divide by 0. So we need to look to see if we've got a common factor. Look at the top of my fraction. There's a delta x in the first part, there's delta x's in the second part, there's a delta x in the third part, so delta x is common. So I can take it out as a common factor. And if I look at it, in the first part, if I take out the delta x, I'm left with 4x cubed. In the second part, if I take out one of the delta x's, I'm left with delta x. So there's my 4x cubed, there's my delta x. Take out the delta x, I'm left with a minus 7, there's my minus 7. So I can see now that I've got delta x's that cancel. So I'll cancel those. And I don't have any problems with fractions anymore because the question now is just a limit as delta x approaches 0 of 4x cubed plus delta x takes 7. If I let delta x actually equal 0 now, it doesn't, but it's so close to it, I'm just going to pretend it did. I'd end up with 4x cubed plus nothing takes 7, which is 4x cubed takes 7. That's what the answer is getting very, very close to. Okay, well, we've done a few examples. Now comes the fun. Time to do exercise 8.2 and 8.3 as quickly as you can. Please enjoy the experience.